if three envelopes are selected at random without replacement, determine the probability that they are all red envelopes. So choosing without replacement looks like there are 1, 2, 3, 4, 5, 6, 7 envelopes. 3 are red. So on your first pick, there are 3 red envelopes out of 7. On your next pick, there are only 2 red envelopes left out of 6 envelopes remaining. And on your third pick, there's only 1 red envelope out of 5 remaining. So just going to multiply these all together. I can simplify a bit. Divide by top by 3, I get a 1. Divide the bottom by 3, I get a 2. These 2's, divide by 2, I get 1. Divide by 2, I get 1. They cancel. And now I'm free to multiply straight on across. So 1 times 1 times 1 is 1. 7 times 1 times 5 is 35. So 1 out of 35 for that one. And then for 57, all 3 children are girls. So, okay. So the probability that the first child is a girl is 1 out of 2. And then the second is still 1 out of 2. And the third is 1 out of 2. So girl and girl and girl. So multiply these all together. So 1 out of 8. And that's that one. For 61, so the Martinos plan to have 5 children. Determine the probability that all their children will be boys. Wow. All right. So they're planning to have 5 children. So the probability of the first child being a boy is a half. The probability of the second child is also a half. Third child, fourth child, fifth child. So multiply straight on across. 1 times 1 times 1, blah, blah, blah. 1. 2 times 2 times 2 times 2 times 2 should give you 32. So that should be good for 61A. And then for part B, they ask if their first 4 children are boys, and Mrs. Martino is expecting another child, what is the probability that their 5th child would be a boy? So they're trying to mislead you in saying there's a 1 out of 32 chance because they'll have 5 boys, but not the case. Every event is independent. Doesn't matter how many boys they had in the past, that's already done with. They've already had their boys. Whatever happens next is a new thing, and the probability of getting a boy now is a half. Doesn't matter what's happened in the past. Everything is independent, and so the probability of their next child being a boy is a half. This first one was different because we didn't know anything about the boys in the past. We just hadn't had any kids, and we wanted to know what's the probability of getting 5 kids that are all boys. And this is a different scenario than the one we're talking about now. So that's 61. And now on to 65. So 65, golf balls. This guy has 7 golf balls in one pocket of his golf bag. 4 Titleist, 2 Top Flight, 1 Pinnacle. 2 balls are selected at random. At least 1 Top Flight ball. Alright, so he has 4 Titleist, 2 Top Flight, 1 Pinnacle, and he wants at least 1 Top Flight ball when he's selecting 2. So he's selecting 2, And if he wants at least one top flight, yeah, all right. That means he wants either one top flight or two top flight, right? He's okay if he gets both of them, right? So long as he has at least one. So we're going to treat this as two separate problems. We're going to find the probability of getting one top flight, and then we're going to find the probability of getting two top flights. Now, let's see. This one's actually tricky because it's, darn it, it's one top flight or two top flights, but this one top flight, he could either do the first one as a top flight or the second one as a top flight. So let's do that. So we have first top flight or the second top flight or both top flight. All right. So this first guy, the probability of getting the first one to be top flight and the next one not, there are two top flights that we want out of 7 total, right? And so there's 2 out of 7. And then the next one, we don't want a top flight in this particular case. So there are 5 possible because we want everything except for the top flight in our next one. So there's 5 of those out of 7 remaining because part A we're doing with replacement. So there's still 7 left. All right. So there's the first top flight and the second not. Now we're going to do the first not top flight. So 5 out of 7 to get the first one not top flight and the second one top flight. I'm saying this too many times. So 2 out of 7 for top flight for the second. And then for the last one, we want them both to be top flight. So 2 out of 7 for the first one and 2 out of 7 for the next one. Again, they're staying the same. The bottom's staying the same because we are replacing it back. So this or kind of tells us to add. So we want this or that or that. So basically, this is 10/49ths plus 10/49ths plus 4/49ths gives us 24/49ths. And that should be our answer for part A. So we will check it. 65, yep, it's looking good. And then for part B, same setup, just we're not going to replace the ball. So we want the first one to be top flight. So there are 2 that we want out of 7. And the next one to not be top flight. So there are still 5 non-top flight balls in there out of 6 total remaining, right? Then the next one, we'll take, say that the first one is not top flight, so there are 5 not top flights out of 7. And then the second pick should be top flight, so there are 2 top flight out of 6 remaining. The last one, both of them top flight, there are 2 top flights out of 7. Then there's only 1 top flight out of 6. Whew, lots of words. All right, so this will be 10 out of 42 plus 10 out of 42 plus 2 out of 42 is 22 out of 42, which simplifies to 11 out of 21. So hopefully that's looking good. Perfect. So last one, number 69. So 69, 2 people who provided information for the table were selected at random without replacement. Determine the probability that at least one had, darn them anyway. All right. So, okay. So I'm going to do this one in a different way because I don't like the way we did it last time. It worked, but let's actually do 65 method 2. So when you see this at least one, I don't know if they taught this in this chapter, which is why I tried to avoid it, but when you see at least one, you think the idea is not none. So we're going to find the probability of getting, in problem 65, no top flights, and then doing 1 minus that probability. So if I want at least one top flight, that means 1 minus the probability of no top flights. So if I want to get no top flights, there are 5 out of 7, and for the first one we're not replacing, so 5 out of 7 for the next. So that would be the probability of getting no top flights, and we'll do 1 minus that, because that's what we don't want, right? Like if there's a 20% chance of getting no top flights, there's an 80% chance of getting at least one. So we're just going to do 1 minus 25 over 49, and that's 49 out of 49 minus 25 out of 49, giving that common denominator. So that is 24 out of 49. So we are matching the answer we got in part when we did it in the other method. This is a lot less work, but the concept sometimes sticks a little bit. So find the at least one is not none. So find the probability of getting none and do 1 minus that. So for part B, if we do that again, so for part B, probability of getting no top flights, if we don't replace, there are 5 non-top flights out of 7, and on the next pick there'll be 4 out of 6. We don't want that, so 1 minus it. 1 minus 20 out of 42. So 42 out of 42 minus 20 out of 42 is 22 out of 42, so 11 out of 21. So again, we match, which is pretty cool. So you can choose which way you want to do it. For 69, I'm just going to do it this way again. So